recording. Okay, here we go. So last time, let's go back and talk about what we just figured out about the energy content between a capacitor before we go on. Okay. So remember that when you have charges on a capacitor, this is going to store some sort of electric potential energy somehow, right? And there was a little calculation we did on Thursday that involves some integration, and then when you do the integration, you end up with this factor of 1/2 that I always forget, right? And so the amount of energy that is stored in a capacitor is 1/2 times the capacitance times the voltage across that capacitor square. And I want to try to bring up this analogy of, well, kinetic energy is 1/2 mv squared, right? Spring potential energy is 1/2 kx squared. So this electrical potential energy, right, is 1/2 c, right, capacitance times the voltage square, right? It's always this kind of 1/2 times some constant times your variable square, right? The voltage is the variable in this case, right? So it's sort of neat that they all kind of follow the same format. And what I'm going to do now is convert this little 1/2 capacitance times the voltage square, right, into the electric field between two capacitors, right? Remember when you have a capacitor, parallel plates, the electric field between them is basically constant. It's approximately constant if you have an infinite sheet of capacitance, right? Right. So you can make this approximation where, oh, the electric field is just the voltage divided by the distance between the two, right? So therefore, right, I can go down to this equation, replace my voltage across my capacitor, right, with the electric field times the distance between them. Well, of course, you have to square it, right? When you do that and massage the variables around a little bit, you get this area times the distance between the plates, the area of the plate times the distance between the plates. And we're going to see this geometrically, right? But you can factor out this E squared, right? And the main thing I want to get you guys to remember is that the amount of energy that is stored, in a capacitor is actually the electric field square. Also, is proportional to it, right? There's some constant in front, right? And we're going to figure out what this constant is today, okay? So if you imagine a parallel plate capacitors, right, you got some plus charges here, some minus charges on the bottom, right? This is the area A, right? This is how big that little plate is, right? The area of the plate. The distance D is the distance between the two plates, okay? So the area times D is geometrically what do you think? What is this? If I multiply this times this, what do I get? The volume, right? Exactly. Volume of the capacitor. I'm going to do VOL so that because there's a lot of V's around, right? Therefore, this factor here is actually the volume. Okay. So what I can do is then, if I just copy the equation over here, oops, no typing. Okay. A times D, right? E squared. I replace this with the volume, right? What I can do is divide both sides by the volume, okay? And then to arrive at this UC over the volume equal to epsilon naught divided by 2E squared. And this is sort of an interesting quantity, right? The energy per volume is known as the energy density, okay? Just like if I have some amount of mass and I have some volume, you want to figure out what my density is, right? You take my mass, you divide by the volume, you get my mass density, right? Okay. Same thing here. You get energy density if you take the amount of energy stored in that capacitor divided by the volume of that thing, okay? And unfortunately, as creative physicists, right, instead of an uppercase U for electrical potential energy, if you put a lowercase u, right, that indicates density, unfortunately, okay? I know there's a lot of u's around and stuff like that, so We're not going to use this too much, but we will run into it when we deal with this thing called electric magnetic field after we cover magnetic fields, okay? So just remember that this equation is important, where the energy in the capacitor is somehow related to the electric field square, okay? That's the important thing, okay? With some factors in front, right? This epsilon naught is just a number, right? 8.85 times 10 to the 12, right? And 2 is 2, okay? Right, before we leave chapter 26, okay, I want to cover one more thing, but that Alwyn mentioned last Thursday, but we didn't get to cover it. So you get to watch it at home on video. Is that what is between these two parallel plates that we just made, right? So by default, what our derivation is, we just assume there's nothing between the two. Okay, when there's nothing between the two, we call that a vacuum. Okay, right? There's just nothing between them. Okay, but you can stick something between the two. Okay, this thing that looks like a stick of butter is called a dielectric. Okay, and what happens when we stick a dielectric between these two plates, it's that it actually increases the capacitance. It makes our capacitors, well, bigger. You can, and therefore, you know, it's actually a, it can store more charge with the same amount of voltage across it. So how does this happen? Why would sticking things between the two things make it better? You would think it'll make it worse, right? Because usually with electrical circuits, you don't want anything between them, right? And then, because you're going to get shocked or something like that. This goes to this idea of a material, if it's not conductive and polarizable, okay? So this so I try not to talk about this dipole stuff, but in this case, we do have to talk about it because it's essential for us to understand how dielectric works, okay? So let's say you have some material that is non-conductive, like a piece of plastic or something like that, okay? Okay. You put that material in some electric field going to the left. What's going to happen is that the molecules inside that material is going to align with the electric field, right? Because basically the positive charge is going to get pushed away from along the electric field, while the negative side of that little molecule is going to get pulled, right? So you basically imagine, where's my ruler? Okay. So imagine that, you know, by default, the inside the material, right, the molecules are not aligned. It's just, this is the positive, this is the negative end. But if I put it through an electric field, what will happen is that the electric field will push this end to your right, right? But since the negative charge goes in the opposite direction of the electric field, right, it's going to pull it to the left, right? So it's actually going to align along the direction of the electric field. Does that make sense? Okay. If the materials are free to kind of wiggle around like that, okay? Okay. So what would happen is that when you put this material between two parallel plates, right? Remember, in two parallel plates, right? If it was in a vacuum, there's just a constant electric field between the two plates from the positive to the negative end, okay? What will happen is that when you put this material between the two, it basically creates a induced charge between the two, okay? And therefore, it partially offsets the electric field that was created inside, okay? You can imagine that when you have this, right? Remember, electric field goes from the positive to the negative. These are like little tiny electric field that was created by just polarizing the material itself, right? Remember, electric field starts on the positive, ends on negative, positive, negative, positive, negative, right? So it points in the opposite direction, okay? This is known as an induced electric field, and therefore, the net electric field between the two plates actually gets reduced, okay? So this is the actual real electric field. This is the external, okay? This is the one that's induced by the polarized material, okay? And we call this polarized material a dielectric, okay? Okay, and that's just the name of it, okay? So why is this useful, right? Um, when you reduce the electric field between the two, you can actually increase the voltage without increasing the electric field between the two. That makes sense, right? Because you're reducing the electric field between these two capacitor plates. And to calculate the effect of this, what you do is you calculate this thing called a dielectric constant, this letter kappa. So the way I write it is basically kind of do a little, that's a really bad kappa. Do a little scripty lowercase k. Does that make sense? I'm trying to write a regular k, but I'm just going to make it smaller. Okay. If you want, if you're having trouble dealing with these weird Greek letters, just write kappa if you want. Okay. Right. And this kappa factor basically quantifies, well, what is the electric field from the outside? Okay. This is the external electric field. This is the real field that you actually get inside. Okay, let's just draw this real quick. Okay, so we have two parallel plates, right? There's some pluses, some minuses, right? These charges is going to create the electric field, not, oops, lost the little bar, right? The amount of charge is going to give you this E naught, okay? Okay, let's just do that, right? But since there's, if you put a dielectric in here, there's going to be a little bit of offset. This is called the E induce, okay? The actual real electric field, let's do that in orange, right? It's still going to point to the left, but it's going to be smaller, right? This is actually the electric field that you see, the real electric field, it's called E. Does that make sense? Right? Because a little bit of the dielectric material is going to try to oppose the external electric field that's actually placed on it. Okay? And this is useful because, let's just get to the equation down here. Okay? If we calculate, let's just skip all this little derivation. If we calculate the capacitance of a capacitor, right, with or without a dielectric between them. So let's say I have a capacitor, right? It has some area, it has some distance between the two, right? And therefore, the capacitor is actually, the capacitance is actually the area times epsilon naught divided by D, right? That's how you calculate capacitor. If I stick a little dielectric between the two, right? Even though it has the same area, has the same distance between them, right? What would happen is that I would get a new capacitor, right? Let's draw the dielectric in green, right? This is the dielectric, right? And it has a kappa value that we're going to talk about what the different material will have. It actually increases the capacitance by a factor of K. Okay? So you basically can make a capacitor that's the same size, but increase the capacities of it by just sticking dielectric between the two. Okay? And hopefully, I think some of you guys saw this, right, where I think one of the smaller capacitor that's like a little cylindrical shape has like almost the same capacitance as the big one, right? Even though it's smaller, because it's actually made of a different material. Okay? And the dielectric constants for various material is here on this little table in the textbook, right? So for vacuum and air, it's basically 1, okay? But a lot of capacitors are made of mylar, so it has a kappa of 3, okay? And if you buy like, fancier electronics such as the ones that are in your phone, you have to make very, very small capacitors with very high capacitance, and therefore you make them out of titanium dioxide or strontium titanate. Okay, these are kind of like expensive metals that you have to, go mine in like Central Africa or something like that. Okay. Interestingly, pure water actually has a very high dielectric constant, right? So why do you think, water is actually bad for electronics? Anyone want to tell me? Well, when you think about water, do you think of it as a insulator or a conductor? It's a conductor. But the thing I said is that, well, for it to be a dielectric, it has to be an insulator, right? The charges cannot move between the two sides, right? So what's the difference between water and pure water? There's ions in it, yeah. So there are impurities like metals and stuff like that, but mainly what happened is that water is actually not made of water. The water we drink, like the ones in your cup, you have H2O, right? But you also have positive ions and negative bases. So these are called bases. Those of you who knows chemistry, these are the acids, okay? And these guys are actually disassociated, so they actually have a net negative one charge and a net positive one charge, so the charge can actually move around. So if you have water that has these disassociated hydrogen and what's OH? That's like oxygen hydride or something like that. Then they, I'm sorry? Yeah, hydroxide, right? Then they can actually carry charge around, okay? But if you have pure water, right, then all of these OHs, right, they're always neutral, so they cannot carry charge around, okay? So pure water, right, is really hard to make. So that's why we tend not to use them, because they also get impurities in them pretty quickly. Anyway, so that's my little spiel about dielectric. Any questions before I try to get a little bit started on chapter 27 next? So I'm going to switch over.